Morning, everyone. Thank you for attending the session on theory of constraints on the Flightline, breakthrough results where it counts. My name is Sridhar Chandra. I'm a partner in Goldratt Consulting. A little bit about Goldratt Consulting. We implement theory of constraints all over the world in commercial and public sector organizations, including the military. Our main mission is to provide extraordinary results to our clients through the application of theory of constraints. So welcome again. Thank you for your time. To provide a little bit of context to this briefing, a couple of years ago in 2019, Headquarters Air Force decided to try out theory of constraints in the Flightline environment, where it is very dynamic and constantly changing with very high variability. So as a result of that initiative, 3 pilots were implemented, one in a KC-135 aircraft at Fairchild, then on the B-1 aircraft at Ellsworth Air Force Base, and at the F-16 platform in Shaw Air Force Base. All 3 of them were implemented in the maintenance groups. Through this implementation, theory of constraints started producing some remarkable results in these pilots, and then Headquarters decided to expand this concept of theory of constraints across the Air Force. So that's where we are. Last year, if some of you attended LOA, the group commander from Fairchild, Colonel O'Connor, presented how they implemented TOC and what kind of great results they saw, remarkable improvement in performance. Today, what I am going to share is a few more case studies, just like the Fairchild, but very different applications. Hopefully, you will find this productive and useful. In terms of the agenda today, I'm going to give a very brief introduction to theory of constraints. Some of you might have already attended the University of Tennessee session on the concepts from Dr. Srini. I'm not going to spend a lot of time on the concepts. I'm mainly going to spend time on 2 applications of theory of constraints. One in the 552nd Air Control Wing out at Tinker Air Force Base, where we applied theory of constraint both in maintenance and in ops. And the second one, applying theory of constraints in scheduled maintenance task, where we implemented this at the KC-135 SPO office, also at Tinker Air Force Base. After that, there'll be some time for Q&A. In terms of going straight into the introduction of theory of constraints, as some of you might have read the goal. If not, I would strongly encourage you to read the goal. It's a very good reading and would be a very useful read for all of you. What TOC is really, it's a management method. It's a different way of managing organizations. It's a different way of problem solving. And the idea behind this method was introduced in the book, The Goal, in the 80s, and it's been widely successful all over the world. What TOC at its core says that any organization is a system. So when you think of a system, and the real leap of faith here is that TOC says that no matter how complex an organization can be, maybe it's a huge wing or a small section or a back shop, it's actually quite simple if you take a systems approach because it's governed by just few elements. So if you are a manager or a leader leading one of these organizations, if you think in terms from a systems look, what as a manager TOC says is that if you can focus on your constraints, that's number one. And number two, if you can focus on improving the flow through the organization, everything will take care of itself. The costs will be better, the speed will be better, throughput will be better, velocity would improve, quality would be better. And on the human side, actually, if you focus on the constraints and the flow, you actually reduce the chaos, firefighting, long working hours, etc., and introduce harmony throughout the system. So that's the fundamental premise of theory of constraints. Look at the system, take care of its constraints, and improve the flow. TOC has been implemented across the world in many different facets of a business. Of course, it started with manufacturing with the book, The Goal, where it was used to improve throughput, on-time performance, cycle time, etc. TOC has also been implemented in the supply chain world where availability is crucial, but at the same time, budgets are very tight. So how do I get my parts available with reduced budget? It's been applied in engineering, R&D, research and technology, new product development to shrink the time it takes for projects and deliver products on time. And finally, of course, it's been applied in almost all facets of maintenance, in the depot maintenance, in the intermediate maintenance, and now in the flight line maintenance. And typically the results that we see is increasing the maintenance throughput, reducing the time in maintenance, and improving the on-time predictable performance. All of it leads to higher aircraft availability to support the mission. One thing to notice here, and this, by the way, the results that you see was compiled by an independent study that looked at various organizations that have implemented TOC. What you see here, what you can observe is that TOC produces big step function improvement in performance. If you implement TOC correctly, identify and attract the constraints correctly, you should typically see a 20, 30, 40, and sometimes even 50% improvement in whether throughput performance or speed or cost, etc. Now, in terms of, again, I'm not going, as I said before, I'm not going to spend a lot of time on the concept, but there are three fundamental frameworks inside TOC. And all these frameworks lead to one thing, which is focus, because in today's world, managers don't have bandwidth to try too many things. So what TOC helps is manage to focus managers on a few high leverage things that can produce extraordinary results. And the three frameworks that are in TOC are: one, the principles of flow, which talks about how to take any organization and improve the flow through the organization. As an example, how do I take a broke aircraft and make it a green aircraft as fast as, how do I flow this aircraft through all my processes? The second framework is the 5 focusing steps. How do I look at my constraints and maximize and leverage my constraints? And the third, there are various tools for identifying the root causes so that we don't tackle just the symptoms. One of the tools that was presented in the University of Tennessee presentation was a current reality T. I hope you had a glimpse of that tool. Again, the purpose is to not solve symptoms, but focus on the underlying root causes. With that, I just want to spend a little bit of time on the 5 focusing steps using a very simple example. You see on the right, there is a small process. This can be a factory or an administrative process or a logistics process or any process that you can think of. And it starts with step E, goes through step D, step C, B, and A. The input is fed into step E, and then the output comes out of step A. It's a linear process. And the numbers on the right side of each of the step is the maximum capacity of that step or the machine or that human resource you can take. For example, E can produce a maximum of 9 pieces per hour or 9 jobs per hour. So if you were the leader of this organization and you are tasked to maximize the performance of this organization, the first question that we ought to be asking is, how much can this factory or this process produce? What is stopping it from producing anymore? So that's the real first step. We call it identify the constraint. In this simple example, it's very obvious. It's machine C, and that is really the constraint. So step 1 is identify the constraint in an organization. Now, once you know the constraint, then actually it is a very powerful thing for a manager, because suddenly it focuses management attention on the constraint. So if you are running this simple toy factory, you would immediately say, okay, I need machine C to be running all the time. And because if I lose 10 minutes on machine C, I will never ever gain it back. My entire system will lose 10 minutes of throughput, and I cannot gain it back. Compared to another machine like D, if I lose some time, I can always make it back up because I have higher capacity. So that's a profound understanding of an organization. So you can do simple things like, I will make sure that the spare parts are available for this machine. I would make sure if the operator is absent, there is a backup operator. I'd make sure everything is ready for this machine to process all the time. So immediately, it's intuitively, we know squeezing the maximum out of machine C is actually how the overall plant would produce. In TOC, we call this exploit the constraint, which is getting the maximum out of the constraint machine or the constraint step. Now, a few more things we can think about in exploitation. One is we also should make, not only should machine C work on the all the time, it should always work on the right priorities. Whatever the customer needs is what machine C should be working on. Anything else is non-value added for machine C. Also, a few more things: you might want to protect the machine C from disturbances or Murphy's law. So you may want to keep a little bit of buffer in front of the constraint C, so that even if there are disruptions upstream, machine C continues to produce. So exploitation is a very critical step of the five focusing process, because it truly allows you to take all the noise out and see what can we do to improve the performance of the constraint. Once we exploit the constraint, the next is, we call it subordinate everything else to the constraint. What does this mean? If you look at this picture, the primary job of machine D and E is to feed machine C. Only what machine C can produce in the right order, in the right priority. Right? So if common sense would tell us that machine D should also produce only 6 per hour, and it should only produce what machine C ought to be producing in that sequence. It does not matter how much it can produce. It should produce only what C needs. Anything else is waste. For example, if machine D only produces 6 per hour, its efficiency is only 60%, but that's okay. By making machine D produce all the time, all we will do is produce unnecessary excess. That's a very powerful thinking, where traditionally we believe that every department, every resource must be busy all the time. TOC will tell you that's unnecessary. In fact, it's detrimental. This is what we mean by subordination. Machine D, for example, could be the most expensive machine in the factory, but it doesn't matter. It has to subordinate to machine C. And the best way to subordinate the factory to machine C is to release material, the input, in the order machine C, not more, not less. By doing that, automatically, the rest of the factory will just be working whatever machine C wants to do. That's what we mean by subordination. Everybody subordinates to the constraint. Nobody is focused on what is important for their own department, but is focused on what is important for the global throughput, or in other words, what is important to the constraint. Once we have identified, exploit, and subordinated, the next step, and only then, we should spend money on improving the constraint. We can put a CPI process on the constraint, or in fact, spend some money and increase the capacity of the constraint, not before. People often jump to this step very quickly before identifying, exploiting, and subordination. This step is what we mean by elevating the constraint. So in this case, we bought another machine. Now step C can produce 12 per hour. Now, once we do that, we know the constraint will move somewhere else. We go back to step 1. And now in this, the new constraint is machine A, and now the whole process repeats again. So this is a very powerful mechanism that any manager can apply in any organization to get a systematic way to improve performance. Okay, moving on to now, how did we apply this at the 552nd Air Control Wing? Before this, in the Flightline, we had only implemented TOC in the maintenance groups, as I said, in Fairchild, Ellsworth, etc. This was the first time when the wing commander decided that he would like to take a holistic view of the entire wing and apply TOC at the wing level, which means both the ops group and the maintenance group work together as a team to implement theory of constraints. And as you can see, the results are even better, because now you're applying at a system which is the wing. When we started working at the wing, we started talking about what is the goal. The wing had actually was in a conversion program. They called it the Road to 48. They needed to have 48 ready crews to support mission readiness. And if you all remember, if you all know, the 552nd is the E3 aircraft, which has multiple crew positions. And they were going through a conversion program where they were merging some of these crew positions into fewer positions. This would allow the wing to ultimately have a lot of flexibility and improve the readiness of its crews for the various missions. But in the short term, it had to go through a massive conversion, multi-year conversion program to convert the legacy crews into the new construct. And the plan was to finish this program by late 2022 or even later. But this was a huge burden on the wing, because not only does it have to take care of its currency and proficiency to meet mission readiness, but also at the same time convert the crews from legacy to new crew positions. The other thing that the wing commander wanted to do was, people were spending a lot of time in training. So the 552nd wing is unique in the way that it also has a training group. The primary flight training is also done at Tinker. So the aircraft are required not only by the ops group for its missions and currency, but it's also required by the training group to as students pass through the training school. Typically, what was happening was, when you look at a PFT or primary flight training, the students would first go through academic sessions, classrooms, and then simulators, and then they would go into flying sorties. What should take about 65 to 125 calendar days was taking more than 130 to 300 calendar days for the students to flow through the training pipeline. And when we looked at it, we found that majority of the time the students finished their academic and sim, but they were waiting for months to get into the flying schedule. And on top of that, they would have a lot of gap between the sorties, so the fly phase would take a long time. And not only that, the incoming was higher than the throughput of the training group. What that meant was the backlog was growing. When we started the project, the backlog was about 200 students in this pipeline and was growing. More backlog means more wait times and longer would it take. And the more time people spend in the training school, the less time they have time in the ops. So it was a huge issue all around. On top of all that, the fleet itself, which is, as you may be familiar, E3 is quite a small fleet. The fleet itself was going through a conversion program from its B model to G model. And therefore, this modernization program means the aircraft were spending more time in the depot to get not only the PDM, but also the modernization program. So how do we achieve this road to 48 and wipe out my student backlog while I have fewer aircraft available to fly? This was the burning platform at the wing level. So in order to do that, when we did an analysis, the core team at the wing did an analysis. In order to meet all the wing requirements, we needed to produce about 1,700 sorties per year. That was the need. Traditionally, they were able to produce 1,200 sorties. That's how much what maintenance could provide. So we went after this gap in two ways. One, maintenance will somehow figure out a way to improve its process and get more aircraft available to produce more sorties. And two, ops group and training group will squeeze more out of each sortie to reduce the requirement of the sorties themselves. How can I make every sortie more, increase the throughput of every sortie? All of this led to the very clear conclusion that the sortie is my constraint. So once it was very clear the sortie is the constraint, it was quite obvious that the next step is to exploit to the constraint and subordinate to the constraint. Okay. So the core team sat down with the leadership team and decided what are the various exploitation actions that we should be doing and what are the various subordination actions that we should be doing. First, we said we should allocate sorties based on the wing priorities. So we established the priority at the wing level. one set of priorities for the entire wing that allows us to use the sorties in the order of priority. Second, we created what is called as role-focused sortie to maximize the throughput of every sortie, to exploit each sortie. I'll talk more about the role-focused sortie in a minute. Third, we also figured out ways where can we remove some of the syllabus from a flying sortie to what is called as a ground sortie, where the students are still inside the aircraft, they get the real aircraft environment, but the aircraft doesn't have to take off. All the systems are up and running. And in the E3 world, a lot of the technicians and the battle management team can do a lot of their training events while the aircraft is on the ground. So we streamlined the syllabus to create what is called as a ground sortie. More to come on that. And then the last thing, E3 is prone to red balls, which means, before it takes off, it might have a maintenance issue. So we created what is called as a fly and a fix window that allowed the maintainers to focus on getting the aircraft flying through fixing red balls in the fly window and fixing the broke aircraft in the fix window. This, instead of going back and forth between fixing a broken aircraft and getting an aircraft to fly by fixing red balls, we created a clear window so that maintenance can focus its resources, especially the 7 levels. In terms of subordination, we created what is called as a low WIP combat plan. What WIP means, work in process. Now, instead of trying to do too many things at the same time in the wing, we said, based on the wing priority that we established in 1, how can we create the minimum number of things at a given time, and therefore maximizing the throughput of the wing. We also realigned the scheduling process completely based on the new priorities, which making sure that the right seats are filled by the right people in the right squadron. Previously, each squadron would get divvied up some amount of sorties, whether it needed or not. Now everything is based on what the wing needs, and it's dynamically assigned at the squadron level. Next, we also controlled how many students would be released into the queue. We didn't stop how many students are coming to tinker, but we did moderated the queue inside the fly phase. And then finally, we had a holistic where we would look at wing level combat plan every month and see how can we recover in case we are getting delayed in execution. Let me talk about a few of the core elements of the exploiting the constraint strategy. They are role-focused sorties, ground sorties, and WIP combat plan. Okay. The role-focused sortie transformed the way the wing decided on the sortie profile. Let me explain how. So if you look at this slide, the light blue portion is the training for flight deck, the pilots, the co-pilots, the navigators. The green part of the sortie is for the battle management team, and the T is for the technicians. Typically, before TOC, they would do what is called as a J sortie. And if you look at it, it's about a 7.5-hour sortie. The blue portions, of course, are where the flight deck gets training. The yellow portions are where the technicians get training, and the green portions is where the battle management team gets their training. Now, when you have so many things packed into one sortie, what used to happen was if anything goes wrong, somebody takes longer, or there is a late takeoff, or some system doesn't power up quickly, it would start conflicting with other roles. And there's no buffer in the system. So while everybody is trying to get something out of the sortie, because of the conflicts, the actual final throughput of the sortie itself was very low. So we moved from the traditional, broad sortie where everybody gets a little bit to what we call it as a role-focused sortie. So now you can see in the bottom, the same 7.5 hours is now distributed into different types of sortie. On the left side, we have a battle management team where majority of the sortie is focused on training the battle management team, which is the ABMs, air battle managers, the MSO, the section leads, etc. And that doesn't mean other people don't get some training, but the focus of that sortie is to get the battle management team getting trained. In the middle portion is the tech sortie, where the focus are now the technicians, the radio technicians, the radar technicians, and so on. And on the right side, it's purely for the flight deck. So by doing that, what we were able to do is for each sortie, we were able to reduce the conflicts. And even if some things goes late or something doesn't go per plan, there was enough buffer. And that actually resulted in a high throughput sortie. They were able to get more sorties, more throughput or training events done using the same time. This is very counterintuitive, isn't it? Because what you try to do is to try to maximize every position for each sortie. And here we are saying you can actually get more by focusing on a few positions. And you can actually think of the entire mission and in a different light. Of course, they had the standard J sortie to take care of some of the things where you have to do it together. But overall, this dramatically improved the throughput from each sortie. The next thing that we did is what we called this as a ground sortie. So if you look at the blue row previously, and this is just a couple of examples, the ARO and ADST, which are the technicians, they would have 14 sorties or 13 sorties, depending on the role, to evaluate. Now, what the team did was took the sorties and said, what can we do on the ground? So instead of everything being a flying sortie, some of the lessons could be done on the ground. The benefit is, of course, for maintenance, it can have an aircraft sitting on the ground to do it. Of course, the aircraft has to be green. Most of the systems have to still be working, but it allows the maintenance to produce the sortie with the aircraft. It allows 24/7 usage of that sortie of the aircraft. And it would also provide consistency in training. Very quickly, we were able to use one tail for a ground sortie every day and really increase the throughput of this process. And while doing so, we removed some of the requirement for flying sorties and by 33 to 35%. This is very powerful because once we know the constraint, we don't want to waste the constraint in doing things that can be done on the ground. This is on top of the sim usage that they were anyway doing. But this is that is a new idea called ground sortie. This was not new. They already knew it. But the minute everybody came to the conclusion that the sortie is the constraint, it became obvious. The ground sortie idea became obvious. The third thing that we did was, as I said before, when you look at on the left side, the picture, these are the various demand for sorties. You have the higher headquarters tasking, you have the conversion sorties, you have the upgrade sorties, we have the student sorties, and the training group and the ops group needed all these sorties. So when you have so many demands, it's very obvious that there are going to be conflicting priorities. So everybody was fighting for each other on the sortie. And many times the sortie would get wasted in a siloed environment. Now with a wing level priority and a low WIP plan, we said we're not going to go after all these things. We're going to focus and finish what is required from the wing level. And instead of trying to get some ABM upgrades or some students going through or some currency. Of course, currency is something that we have to maintain, and that is in the bottom row of the right chart. But everything else we prioritize and sequence it. The beauty of that is when we prioritize and sequence it, and in combination with the role focus sorties, the plan that we came up with was much, much faster than what they had done before. For example, the conversion would have been done by May instead of 2022 late. So that is the beauty of a low WIP, highly focused combat plan. Okay. On the maintenance side, so just to recap, three main things: role focus sorties to improve the throughput of each sortie, ground sortie, and the low WIP combat plan. These were the three big elements of exploitation and subordination on the ops side and the training side. On the maintenance side, of course, the goal was to increase the aircraft availability, We did that by focusing on the few precious resources, the 7 levels and the 5 levels, on fewer number of aircraft at any given time. We reflowed the schedule maintenance. We did something called as bundling, more to come on that on the later sides, to reduce the touch time. And we went after some of these big jobs like home station checks and ISO to shrink their time. So the goal was to improve the available aircraft to fly by going after schedule maintenance improvements. But we all know when we release more aircraft to fly, more aircraft will break, because V3 had a very high break rate. So not only did we had to improve, give more aircraft back, we had to improve the rate at which we fix the aircraft. So we worked on the unscheduled maintenance side. I talked about the very clear fly and fix window. And also we focused on resources on fewer aircraft on any given time. Rather than spreading them thin across multiple broke aircraft, we decided a maximum number of aircraft they could work at any given time, focus them and finish one aircraft and then pick the next aircraft. Now, a few more things that we did on the maintenance side is, because of the high red ball rate, sometimes the red AMU and the white AMU would have different aircraft in red ball. So we formed a single queue system. The first aircraft will go to one AMU, the second aircraft will go to the next AMU. Instead of red AMU working on just the red aircraft and white AMU working on just the white aircraft. By focusing that very clear single queue system, we were able to really fix these red balls at a much more faster rate rather than spreading thin. Also, we came up with some clear rules on when to use the spare, when to step out from the current aircraft and go into the spare, when not to do it, and so on. And also focus the 7 levels on fixing the red balls. By doing that, we were able to reduce the delays and groundabouts and so on. Not the groundabouts, just the late takeoffs and delays due to red balls. And as I said in the previous slide, we said that for every aircraft, we will have a 7 level, a 5 level, and a 3 level. Of course, for some jobs, we could work with one 7 level on 2 jobs, but we said that's kind of the team for every aircraft. Once we have this team, we'll go work on that aircraft. We'll rapidly fix that aircraft, go to the next aircraft, and so on. Okay. We also worked on the ISO flow. In order to keep the WIP low, we had to bring the ISO flow down from 15 days to 12 days. And instead of creating a detailed ETIC driven schedule, we created an aggressive schedule, but with enough buffer in the end. And which allowed us to plan more aggressively without impacting the quality and scope of the ISO. So that was the goal, to reduce the ISO flow by 20%. In fact, the second ISO, we were able to beat that. Okay. Now to the results. By implementing theory of constraints, just to give you a perspective, we started the project late August, early September. And we went live the first 2-3 months. We brought the team together, designed the solution, changed the processes, and we went live in November. And the bars that you see in the left is the number of evaluations, or this is the student completions in a simple way. And very quickly in November, we saw a jump. In December, we saw even bigger jump and so on. So you can see there is a big jump immediately after we went live in terms of what the throughput could be produced for the wing. Of course, depending on what kind of crew position are coming out, these numbers will fluctuate, because some crew positions will need more aircraft, more sorties, and some will need less. But regardless, there was an immediate improvement of performance. We also started measuring how effective is the sortie. And we had various measures. And what we found, the sortie effectiveness, which is how many did we plan and how many did we get out, almost went up by 90% from before TOC to after TOC. Okay, so that's the performance of throughput performance at the wing level. As I said before, the main goal was to achieve the readiness for road to 48. When TOC started, there were out of the 912 crew positions that is needed for 28 crews, the wing had 356. In a few months, we have come down to 643 positions ready to go, while maintaining the currency of all the crews. And the conversion program is on track to be finished by May or June this year. And we will be able to wipe out at the current rate of throughput, we can wipe out the throughput, the student backlog in the training group by end of this calendar year. Remember, originally it was supposed to take at least a couple of years to finish the conversion. And the student backlog was actually growing. If we continue on this project, we will be able to, in fact, wipe out the backlog so that students are not waiting for training. Okay, this is remarkable performance. From the maintenance group, as I said, the first goal was to increase the availability of aircraft. Since the model that we needed to fly was the G models, our goal was to go from 5 aircraft available every day to 7.5 aircraft. And we have been consistently releasing 8 aircraft every day to fly. In January, it was 8.5. And remember, that means we have released 3 additional aircraft from a fleet of just 14 G models. And on the other side, when we release more aircraft to fly, more will break. So previously we would be able to fix 3 aircraft a day. Now we are fixing 5 aircraft. And of course, this is averages because some will be easy fix, some will be difficult fix. But on an average, the rate we are able to fix is 5. So on top of this, we have completed the HSCs, which you take in 2 days to in 1 day. And the second ISO, in fact, we have completed in 10 days from the original 15-day plan. So as you can see, this is a step jump performance improvement, both from the ops side as well as in the maintenance side. Moving on to the next case study, this was done at the KC-135 SPO office, and the focus again was a KC-135 platform. Now, I'm sure many of you are familiar. Typically in scheduled maintenance, you involve what is called as a big job. Big is not an exact technical term, but just for clarity. You have jobs that take multiple days or even weeks. Like in the case of KC-135, you had a PE or ISO inspection that used to take 30 days. Now they take 12, 13 days. A 900-hour inspection, which used to take 3 days. Now it takes 24 to 36 hours and so on. And you have all these big inspections. And then there is a whole bunch of small inspections that you go called SIs or multiple inspections, TCIs, time control, some CBM plus activities, TC2Os can be big or small. When we first implemented in the maintenance group last year, we first went after the performance improvement in the big jobs. We saw 50 to 70% reduction in the time it takes to finish the big jobs without any impact on quality. Then we focused our attention on the small jobs, and that's what I'm going to talk about today. So this is just a hypothetical scenario. If you take a single aircraft and you look at this line, think of it like a timeline. At the 2 extremes are the 2 PEs or the 2 ISOs that's done once in 2 years. And then along the time, you do a whole bunch of inspections along the way. Some of them are very small, half an hour, hour. Some of them are a few days. But that's what every aircraft goes through. And each of these inspections fall due at a certain time interval or an hour interval or a cycle interval, depending on, and it will vary for aircraft to aircraft to aircraft. Okay. And what we typically do is we try to make, in the traditional maintenance world, we try to not do the scheduled inspections ahead of time. So we would wait until as close as possible it's due, and then we would do the scheduled inspection, because the thinking is if I do it sooner, I'll do a lot more in maintenance. But when I translate this idea into multiple aircraft, let's say you have in this example, you have 20 such aircraft, and things are lining up this way. On any given day or any given week, you will find that multiple scheduled inspections fall due. What does that mean? That you have to send your resources to do all these inspections to avoid an overfly status. Okay. And this translates into very high WIP, which means you have to take care of all these scheduled jobs on top of course, the unscheduled maintenance that you'll have to do. Now, when we did an analysis in Fairchild, and we did this for multiple bases. We did it for MacDill. We did it for an Air National Guard base, which has a fewer aircraft. And we found the same trend. If you see this chart on the left, the x-axis is each flying day. And we took a 2 or 3 month window last year and plotted on each day what are the activities that are due, the scheduled maintenance. We took out the big one like the ISO or the PE, and then we plotted the rest. On the y-axis are the various tail numbers. Of course, I made it 0 to 60, and Fairchild has close to 60 aircraft. What you see is this chart with all these dots. Each dot means a certain job is due. The scheduled maintenance job is due. This is not even counting the delayed discrepancies and the broke aircraft. So what we found out that on any given day, average they were touching 7 aircraft, and the same kind of big numbers for other. Of course, Fairchild has got a lot of aircraft, but even for smaller bases, they found out that they were touching too many aircraft. And in a 60-day period, if I look at on this dimension, if I slice it horizontally, you can see how many times an aircraft keeps coming back to maintenance. So on an average, they're touching 7 aircraft per day. But if you look at the histogram on the bottom right, you see more days. There are days with even 8, 9, 10. About 78% of the days, there are more than 4 aircraft down for scheduled maintenance. Now, one can argue these are small jobs. It may take half an hour, but we know in maintenance, nothing takes quick. First of all, you have to assign the resource, the right AFSC skill. They have to go to the tool room. Then they have to be transported to the flight line. They have to do the job, come back, and they may get pulled off in different ways. So everything takes time. And as a result, when you have this high work in process, it takes away capacity from unscheduled maintenance. It results in multitasking of resources between jobs, especially the key 7 levels start spreading thin between scheduled maintenance and unscheduled maintenance and multiple priorities. The management team, the production team, lead pros, pro supers, expediters, now they are trying to juggle all these jobs. And of course, the aircraft are waiting on each other because we always have only limited people to do the jobs in limited time. So when you have very high WIP, it causes multitasking, which immediately has a big impact on maintenance throughput, speed, and quality. So we introduced this simple idea called bundling. The idea behind bundling is not very new, but how can we do bundling in a structured process? So what you do, anytime an aircraft comes down for a scheduled maintenance activity, you look ahead 30 days, 20 days, whatever, and there is a science behind this. Applying very simple math, we can decide how many days we can bundle ahead and pull in all those tasks and do it together. And now you, instead of bringing the aircraft multiple times, you bring it only once, focus a team, and get it done. And today we can again do a math and calculate how many aircraft do we need to bundle every day, and how many days do we need to bundle. By doing that, instead of within a way, and you will be able to reduce the WIP for maintenance. Not only that, it frees up the aircraft for ops. Now, there are multiple strategies for bundling. For the sake of simplicity, broken into dynamic bundling and fixed bundling. In dynamic bundling, you take a certain aircraft and bundle for X days. Then you take the next aircraft and bundle for X days, and so on. Of course, you can ask engineering guidelines, and the bases decide how to do this. In the fixed bundling, you use some pre-existing bundles and latch on the small task and attach it to them, or create some new bundles. So either model will work. In the case of KC-135, we sat down with the engineers at the SPO, and we also had the representation from active duty, Air National Guard, Reserve, the lead pros, and some subject matter experts. And we took all these tasks, which are falling in a 2-month inspection, 6-month, 3-month, 12-month, 60-hour. You can see these various jobs, and we bundled it inside pre-existing bundles. So we took all those blue jobs and put it inside a 900-hour once a year. We took that HPO. And while making so, we made sure there are not conflicts. We made sure the package is not becoming big. We did a few proof of concepts, and people were able to easily fit it in, and so on. So that was the model that we applied using the the knowledge of the engineers plus the subject matter experts in the field. And this is the strategy, as I said, we employed for KC-135. We inputted this into the GO81 program. So if you look at the descriptions of these tasks, now they say to be bundled inside the 900 hours or inside the pre-flight or inside the HPO, etc. Okay. And what we have seen is immediate results. So on the left side is the picture that I showed you before, with an average of 7 aircraft in scheduled maintenance. This was the last June to September. On the right side, Fairchild started implementing this late November. And in January, you have already seen that the WIP has come down from 7 to just over 4. And what you also see, the number of days that are 1, 2, and 3 are significant. And slowly the tail, as they go through the fleet 1 or 2 times, what we are seeing is that you no longer have those days with very lot of aircraft down for scheduled maintenance. You see that the tail of the histogram is shifting to the left. And this is very powerful because this is a simple solution that very quickly resulted in 3 additional aircraft available to fly. Okay. Now this idea has been applied, is being applied in Shaw in the F-16 platform. They have seen remarkable improvements in WIP. It's been applied in the F-15 platform at Kadena. So this bundling idea is very powerful because it takes care of all these small things. Now you can go even one step further. When you bundle, you can bundle some of the DDs, some of the CBM plus tasks. All these are opportunities for bundling. And it cuts the WIP, frees up the aircraft for flying, and immediately releases multiple aircraft. That's what all these bases have seen in terms of aircraft availability. So just to summarize, working with the maintenance community and the engineering team, we are able to tackle the small scheduled maintenance job through this concept of bundling. And the ultimate goal is to reduce the number of aircraft in schedule and maintenance at any given time and improve the availability of aircraft. Thank you very much for your time and attention. Now I'm ready for questions.